solve another Leetcode problem, 864, shortest path to get all Ks. Yeah, let's try to understand the problem. So we have the dot, it means empty cell, so this is a dot. And we also have this hash sign, so this is a wall, so this is a hash. And for this at, so this is the starting point for this person. As you can see, this is going to be the starting point. And this starting point can be anywhere. And the lowercase letters represent Ks, and uppercase letters represent the logs. So this is the lowercase, and this is the uppercase. And for each lowercase, and there is an uppercase letter. So for example, there's a lowercase a and uppercase a, so this means the K and log. So for another one, it is a B and uppercase B, and this means, for log B, the K is for this B. Yeah. So this is the basic meaning. Now let's go through the problem. Yeah. So you start at the starting point, and one move consists of walking one space in one of the four cardinal directions. So this means this person can go to 4 directions. Yeah. You cannot walk outside the grid. It means you cannot go out or walk into a wall. So you cannot go inside the wall. Yeah. So if you walk over K, you can pick it up. So for example, if you go to here, you can pick it up, and you cannot walk over logs. So for example, if you pick up this K, it means you're gonna collect this K, but you cannot use this K to unlock this one. You have to use this K to unlock this one. So this is the meaning, because they have a pair, this pair and that pair. Yeah. And we are going to, so if you walk over K, so this is the meaning. So you have to use the K to unlock the corresponding logs. So yeah, so for some K from more than or equal to 1, less than or equal to 6, there is exactly one lowercase and one uppercase. So this is meaning one lowercase a or one uppercase a for the logs of the first K letters of the English alphabet in the grid. Yeah, so this means definitely this is going to be a BFS problem. If it is a BFS problem, we're going to check and the value of this K. So this means the K is a smaller value. Normally, we can use a bit mask BFS to solve the problem. So this is the information. This means that there is exactly 1 K for each log and 1 log for each K. Yeah, so this is the meaning. And also that the letters used to represent the Ks and logs were chosen in the same order as the English alphabet. This meaning just means we have an order of this character A, we can use it to unlock the log A. Maybe we have a B, and we can use this B to unlock this B. So this means for this K, we have to lock this one first, and then we're going to collect this K. Yeah, and we're going to return the lowest number of moves to require all Ks. So we're going to collect this K and this K. So how many moves? 1, 2, 3, 4, 5, 6, because we can use this K to unlock it. 7 and 8, so we're going to return 8. Now let's check another example. So for this example, so we're going to return a 6 because 1, 2, 3, 4, we can unlock this one, 5 and 6. So we're going to need 6 steps. And for this one, it's going to be -1 because we can never unlock this log because we never have this K. Yeah, according to the image. So now let's try to understand how to solve the problem. Yeah. So normally for grid, so there's a person. This person can start at any position, and at some areas maybe there are walls at these areas or walls at these areas. Yeah. But maybe some areas they're gonna be. So for example, this is also a wall. And maybe this is a K, yeah, and this is a log, and this log is directly designed for this K. Yeah, maybe it's gonna be something like this. Definitely, we're gonna start from this person, and we're gonna start to from 4 directions. We're gonna use the BFS to solve the problem. But how can we design the weighted set? Yeah, because for this person, for example, this person can go forward and go backward. Yeah, because for this image it is okay, but let's just check another image. So let's just check this one. So the person can get this k, but maybe there's another lock. Maybe the lock is not there. Yeah, it's difficult to make another drawing, but definitely for this person, there's a person. This person can go forward and go backward. It doesn't mean this person can only go from one position. So let's start to check this this one. Yeah. So this person gonna collect this k. So maybe what if this k is not here? Yeah. Maybe this k is at the corner at this areas. So this is my k. So there's no k here. So the person gonna go from here to here and collect this k, and this k is for this lock. Yeah. And this k is for this lock. So the person definitely will go forward and go backward. It means the person will some areas, some of the cells of the grid, the person may go forward and backwards at least 2 times. Yeah, or maybe more time. So this means we need to define the state. It means if the person collect this k, it's a new state. So for example, there is a k here. So before the person collect this k, so currently the state is 0. So this means we're gonna define the state. So the state is dependent on the lowercase characters. So for example, if we have a character a, b, c, f, and here is a f. Yeah. So we're gonna use bit mask to define our initial state. So the state means for different positions for the character, for example, a, b, c, f. If we have a, b, c, f, it's going to be 1, 1, 1. There's no d, e, so it's going to be 0, 0, and 1. So this is going to be the state of the case. Yeah. So the person, before the person collect any case, so the state is going to be 0. It means there's no case. There's no a, b, c, or f. Yeah. And then the person continually to collect the case. If the person click a k, for example, this case a, so it's going to be updated to a new state. Yeah. So for example, it's going to be 1, 0 if we only have 2 cases. Yeah. So if the person unlock this one and collect another k, so the state is going to be 1, 1. So this means this is another state. Yeah. So this is used to design a visited set for our BFS. So before we get 1, 0, it is just a 0. So it means our state is 0. So this person can go somewhere. But up to here, while this person collect this k, so it will go to a new state. So inside this new state, we're going to continue this BFS. So continually, this person can go forward and backward 4 directions. Yeah, and then the person will go down and to check this lock. But this lock, we don't have that k. If we don't have this k, so that is okay. We will not go this directions. Yeah, but the person will go this directions because we have the k. So we will unlock it. And then the person will still go for directions. But this has already been visited because our current state is only 1k. Yeah, and then the person gonna collect this k. So it means have a 2 case. It's another state. But if the person have 2 cases, it means we've already collected all cases because the total number of cases is 2, and now we collected 2 cases. So it means we've already reached a final state. So at this position, we're gonna return how many steps. We can code it like 1, 2, 3, 4, 5, 6, 7, and 8. Yeah. So this is gonna be the whole process for the problem. So we're gonna define initial state is going to be 0, and the final state is going to be 2 to the power of n. So 2 to the power of n. Yeah, 2 to the power of, let's use this, 2 to the power of n minus 1. So this is going to be the final state. Yeah, it means at each place it's going to always be 1. But the initial state at each position is going to be 0. So we're going to use this kind of state to represent at which position this k has been visited or not. So 1, 1, 1, 1, 1. It means all those 5 k's has already been visited. So the state is the final state. Yeah. So we just need to check how to go from state 0 to 1, 1, 1, 1, 1, the final state. Yeah. So for this kind of the problem. Now we're gonna start writing the code for the problem. Definitely it's gonna be a lot of definitions. So we're gonna define the row and column and also the directions, because we can go to 4 directions. And it's gonna be length of the grid and length of the grid 0. And we're gonna define that 4 directions. It's gonna be 0, 1, 0, minus 1, and 1, 0, and minus 1, 0. Yeah, so this is gonna be the 4 directions and row and column. Yeah. Now we're gonna find the starting position. We're gonna find this person. So where is this person? So we're gonna use X and Y to represent this person's starting position. Yeah. So I'm gonna use an array. Inside it's gonna be a tuple. So it's gonna be RC, and for R in range capital R. So for C in range capital C. So if this grid RC equal to the character at, so this is gonna be the starting position. And we also need to count how many cases do we have, because we need to define the state. So we're gonna use n as the number of cases. So we're gonna check it. So it's gonna be I'm gonna use a 1 for R in range capital R, for C in range capital C. So if grid RC dot is lower, so if it is a lower character, so basically it means this is a K. So I'm gonna collect it, and we are also sure all the cases gonna have a pair with the lock. Yeah, so there's 1 K for this lock and another K for that lock, and we are sure about that. So we just need to count how many Ks. Yeah, and there's no duplicate case. For example, for this lock, it never has two Ks for this lock. Yeah, it is just 1 to 1, because it is set exactly 1 K to 1 lock, 1 lock to 1 K. Yeah, it didn't set that this lock can have 2 Ks. Yeah, only 1 K, 1 lock. Now we've already called how many Ks, and we can design the queue and the weighted set. So for the queue, it's gonna be a dequeue. So inside it's gonna be x, y, and my initial state is gonna be 0. And also for the weighted set, so I'm gonna define a set. So inside it's gonna be x, y, and the state is gonna be 0. Yeah. Now I'm gonna prepare a result, and it's gonna be 0. So we can go through for the BFS. So while q for anything, let's just use underline. So for anything in range length of the queue. From here, we're gonna pop. Yeah, so let's just use x, y, and state. So we're gonna pop out the position and the state. So coast dot pop left. So we're gonna pop it out. Yeah. Now we are going to check the 4 directions. So for dx and dy in 4 directions. So we're gonna update the new coordinates. So row and column gonna be x plus dx and y plus dy. So this is gonna be the new coordinates. Yeah. So let's just check if we go out of the for loop. So the result should be plus equal to 1, and the final result gonna be minus 1 if we didn't find it. Yeah. But from here, what about if we find it? So we're gonna check this state. Yeah. So if the state equal to 2 to the power of n minus 1, yeah, we can write it use a bit mask, because we used the bit mask. Maybe we, yeah, we can write like this. So 1 left shift to n positions minus 1. So this is gonna be the state. If this state equal to the final state, it's gonna be 1, 1, 1, something like that. And we're gonna return our result. Yes. Then we're gonna check the 4 directions, and we're gonna check the boundary if it is inside of the boundary, if row and column inside of the boundary, and similarly for the column. Yeah, if it is inside of the boundary, we're gonna take the grid out, so row and column gonna be a character C. Because later on we're gonna use this grid, row and column many times, so we're gonna define it as a character C. This is gonna be easier for writing the following code. Yeah, and from here it is okay. Yeah, so definitely I gonna use the state many times, so I'm gonna prepare a next state. So this next gonna be my state. Yeah, and later on I'm gonna use this next state many times, so I'm gonna define it here, and later on I'm gonna use this state. Yeah. So I'm gonna check this character. Yeah. So if this character is a hash, what about if it is a hash? It means it is a wall. Or or if this character is a lock and we don't have the case. Yeah, if it is a lock, it doesn't mean we cannot go through it. If we have the key, we can still go through it. Yeah, so we're gonna check if it is a lock. So if this c dot is upper, so this means it is a lock, and for this lock, it must. So for this lock, we must not have this case, so it means we doesn't have the key. So if we have the key, we can go through. So for this tag, if it is a wall or if there is a lock and we don't have the key, so how to represent that we don't have the key? So we're gonna use a bit mask to represent it. Yeah. So it's gonna be let me try to write the state for it. So we're gonna check our current character. So our current character is gonna be odd this character C minus this odd A. So this is gonna be the position of the character. Yeah. So let's put it inside, and it's gonna be shifted shifted to how many positions? Maybe this character is capital A, so it's gonna be move one position to the left. Yeah. But what if it is A, it moves 0 position. If it is B, it moves 1 position. Yeah. We just need to check at this position. We're gonna compare it with our state. So we're gonna use the next. Yeah. So the next is the state. Yeah. So we're gonna use next add. We're gonna use the next add this one to check. Yeah, we're gonna use the next check with this bit. So this bit is 1 definitely, and if the next at that bit, maybe we're gonna check it here 0 0 1. We're gonna check this bit, and this one shifted maybe 1 2. Yeah, 2 times to the left, maybe at this position. So definitely here is a 1, and this is our state. We're gonna check it with the state. If this one and the state, it is 0. So this means, we don't have the key. But what if it is 1? It means we have the key. But currently we are checking if we don't have the key. Yeah. So it means if it is equal to 0, yeah, let's just put a parenthesis for it, just keep it safe. Yeah, so if this equals to 0, this means for this lock we don't have the key, and also maybe some areas this is just a wall, so we just use a continue. We're gonna continue it. Yeah, now we're gonna check. Now definitely it is okay for us to check other cases. Now we're gonna check if it is lowercase, it means it has a k. So if c dot is lower, so this means at this position, this is a k. So what are we gonna do? If it is a k, definitely we're gonna collect it. Yeah. So how to collect a case? Yeah. Similarly, it's like the bit mask operation. So before that, here is a 0. Now we're gonna set it to be 1. So how to set this bit to 1? We just similarly use this idea and shifted 1 shifted left. How many positions? We're gonna end the next state. Yeah. So let's try to write it. So the next state gonna this is not end. I'm sorry. This is or because we're gonna add it to our state. So we're gonna use the bit or. Yeah, because we want to put that bit 1 at the state. So we're gonna use the or operation for the bit mask, and let's just copy these areas. Yeah, let me just write it. Maybe copy gonna make a mistake. So it's gonna be 1 shifted with odd c minus odd with the lowercase a, because for our k it is a lowercase, and this is just for log it is uppercase. Yeah. So we're gonna put it into our state. It means we've already collected this case. Yeah. Now definitely we're gonna put it inside the queue and visit set. Yeah, but we have to check if it is inside the weighted set or not. If it is not inside the weighted set, definitely we can put it inside. Yeah. So we're gonna check if this row, column, and the next state not inside the weighted set. Yeah. So we're gonna put it inside. Yeah. Definitely for here, I combine the code together because this is just for the case. But what if it is empty? If it is empty, it is still okay. So for here, I'm checking them together. So I'm gonna directly checking if it is not in weighted set. It means if it is a lowercase, it is okay. We're gonna add it, and then if it is not inside the weighted set, we're gonna put it inside. But if there's no lowercase, it is just an empty space. We're gonna still put it inside. Yeah. So Q should append with row column and the next state, and the weighted set gonna end row column and the next state. Yeah. So this is gonna be definitely this is gonna be the entire code. Yeah. It is a lot of things we need to consider, and definitely for here, these are just the basic definitions. I think we can write it easily. And the difficult part is about how can we design this queue and weighted set. And we're gonna use a bit mask, and we're gonna use a state, and we're gonna try to update the state, and we're gonna put the new state inside the queue and weighted set. And for here, we're gonna check how many steps. And here is if we find the final state, we're gonna return the result. Yeah. Now let me run it to check. What is wrong? Yeah, for here I did something wrong. Because this is an array, inside an array there's a tuple. So for this tuple, I'm gonna pop out the tuple, and then I'm gonna take the value of x and y for the starting position. Now it seems it is okay. Now let me submit it to check if it can pass. Yeah, as you can see, it passed, and it is just 0.2 seconds. It means it is okay. Definitely, it is okay. Yeah. Now let's try to analyze a little bit about the time complexity, and how can we analyze the bit mask with BFS time complexity. Yeah, normally for BFS, it is okay. We can definitely use R times C as our time complexity, and this R and C, it is 30 times 30, it is okay. Now we have this kind of a bit mask, and what is the value of the bit mask? And let's just calculate it. So it's going to be 2 to the power of 6 because maximum they're gonna be 6, because k is more than or equal to 1, less than or equal to 6. Yeah, and it's gonna times 30 times 30. So this is gonna be the final time complexity. So let's calculate. This is just 900, and 2 to the power of 6, it is 64. Yeah, so this is gonna be basically 6 times 10 to the power. Yeah, maybe this is let's just make it 100. So this is 100, and this is 1000. Yeah, so definitely it is 1 times 10 to the power of 5. So that is why it is so fast. Yeah, so if you don't use the state as the bit mask, it's gonna be time limit exceeded. Basically, there will be a lot of situations and a lot of things you're gonna put it inside the queue, and you're gonna never get a solution because it's gonna be time limit exceeded if you don't use the bit mask, or if you don't use the state to solve this BFS problem. Thank you for watching. See you next time.